Let's walk through one example from lab 8. That's the first op-amp lab. I want to show you how I wire things up, kind of how I organize my wiring on the breadboard. So I wanted to pick one part of lab 8 to do a little video about. And the one I decided to pick was the op-amp integrator because it's if you only do one thing from lab 8, with the real hardware, I recommend that you do the integrator. So let me just, okay, here it is. Yeah, so it's part 4 on integration from lab 8. So let's just talk through how that works. First, let's just talk through how the circuit works. So initially, I want you to pretend this, I call it the bleeder resistor. Pretend this 1 mega ohm resistor is not here. Well, we'll see in a minute why it is here. Okay, so then we just have one resistor R at the input and a capacitor C at the output. And so remember our two golden rules. So the first golden, actually I don't remember which one's called number 1, which one's called number 2. But one golden rule of the op-amps is that the inputs draw a negligible current, okay? So we'll just pretend it's absolutely 0 right now, and then next week we'll see that it's a very small but measurable number. So the inputs basically draw 0 current, and then as long as negative feedback is working, which means that a portion of the output is fed back into the inverting input. So this is called the inverting input, and this is called the non-inverting input. So as long as a portion of the output is fed back into the inverting input here, then the output will do whatever it can to ensure that the two inputs are kept at the same voltage. Yeah, we'll see again in the next reading assignment how that works, the math behind how it works. But okay, so inputs draw no current, and as long as feedback is working, the two inputs, the output somehow does whatever it needs to do such that in order to keep the two inputs the same. So we've grounded the non-inverting input. That's a pretty common configuration. So we see this also in the inverting amplifier. So we've grounded the non-inverting input, which means that as long as the feedback is working, the op-amp will do its best to keep the inverting input at 0. So then we call this a virtual ground. See, because pin 3 really is grounded, the non-inverting input. And the op-amp's going to try its best, and it usually succeeds. It's going to try its best to keep the inverting input at ground. So it's not a real ground. We call it a virtual ground because it's grounded only by virtue of the fact that the op-amp is working. And if you actually, if you have a circuit that has a virtual ground, if you kill the power to the op-amp, or if the op-amp output is stuck at plus or minus power supply, or if you forget to connect the feedback, you can check and see if this virtual ground is really ground. And if it's not really ground, then you know there's something wrong. Anyway, so because this inverting input is held at virtual ground, then it's very easy to see what the current is through this resistor. We just have that this input current, I, is V in over R, okay? Because this is 0, there's V in, so Ohm's law says V equals IR. So okay, so that's pretty easy. And then, because, okay, so we're pretending this big resistor up here is not present. So ignoring that big resistor, just it's not there, then the only place is, because the inputs draw a negligible current, the only place that current can flow is through here. So it's the same current I flowing through the capacitor. And then you remember for a capacitor that Q equals CV. And we can take the time derivative of both sides of this. So the rate of change of charge is current. So we say I is, and the capacitance is constant. So I equals C dV by dt. So that's the voltage. So basically what that means is, so this is right, this is one capacitor plate has charge plus Q, one has charge minus Q, and this is the voltage across the two plates. So then the rate of change of that voltage across the two plates is the current through the capacitor. Now, when you think about what's the sign, so imagine that the current is flowing from left to right here. So in other words, toward the output. If the current is flowing that way, then you'll have positive charge on this plate and negative charge on this plate, right? Because positive charge is flowing into here. So this plate is going to be more positive than this plate. So that means that the output, so this voltage is held at 0 by the virtual ground, so this output will become negative. Okay, so actually the more current flows from left to right here, the more negative V out becomes, to get the sign right. So actually, this is really I equals the capacitance. This is minus the capacitance times dV out dt, okay? Because as this current flows to the right, V out will get more and more negative. Okay, and then we can just plug in the value for I. So this is V in over R is minus C dV out by dt. So then we have finally dV out dt is minus V in over RC. And then we can just integrate both sides, and you get that V out is minus 1 over RC, the integral with respect to time of the input voltage. So that's kind of cool. Okay, and again, this is the R and this is the C. Now, you know that the op-amp outputs can't get more positive than the positive power supply or more negative than the negative power supply. In fact, in most op-amps, for example, in the 741, they can't even quite do that, so they can't get closer than like about a volt to the positive and negative power supply. So for the 741 powered by plus or minus 9 volts, we'll see that you can't get bigger than about plus 8 volts or smaller than about minus 8 volts, roughly. So suppose you have like a tiny little input, you have like a 1 millivolt input, and you wait a long time, then eventually the time integral of 1 millivolt will be, you'll be stuck at minus 8 volts here. So you don't really want that to happen. So imagine, you could also imagine that there's some finite input voltage applied for a while, and then you stop applying it. So you apply a finite input voltage for long enough that the output reaches some, the biggest or smallest possible value, and then now you set the input voltage back to exactly 0. Well, you want somehow to clear that memory out of the capacitor. You want to bring it back to 0. So one way to do that is you have a little switch up here. So you could, it's actually pretty common to stick a switch up here. I want to draw that, yeah. And then you can like close the switch, and that removes the charge from the capacitor. Then you open the switch and start integrating. So that's what you do if you, you know exactly when you want the integral to start, and you want it to start at some fixed time and maybe end at some fixed time. But sometimes it's inconvenient to do that. You just want things to go on steadily. So you have this very big resistor. I call it the bleeder resistor because it kind of lets the charge slowly like drip or bleed out of the capacitor. So this is a really big resistor. So basically, if you imagine that there's no input, imagine V in is 0, but there is already some charge in the capacitor, that charge in the capacitor will discharge with a time constant of this big R bleeder times C. So it just kind of drains it back down to 0. So this just guarantees that on very long time scales, if there's no input, then the output comes back down to 0. That's all. So it's a big resistor. And actually, if you remember the inverting op-amp, remember the inverting op-amp, there's a resistor here, and there's no capacitor. So then the DC gain of the inverting amplifier configuration is minus this resistor divided by this resistor. So you can kind of see, let's see, so if this were 1 meg and 1 K, that would be a gain of 1,000, so it's actually a gain of 200. Yeah, so actually, if you have a small DC input voltage there permanently, then the output must be like minus 200 of that small DC input voltage. Because, yes, if you had like a 1 millivolt constant input, I think you would get an output of minus 200 millivolts, because 1 meg over 5K is 200, if you remember the inverting. But, okay, I digress again. So now we want to wire this up. And one thing to notice is that this op-amp, so far we've just dealt with pretty simple 2-terminal devices. They don't have any external power. In the case of the op-amp, the output can often, deliver more current or more power than the input. And you say, well, how does that work? What does Mr. Kirchhoff say about that? And it comes from the power supply. So this is a device that basically requires external power, and then what it does is controlled by these inputs, but the real current that comes out of the output is coming indirectly somehow from the power supply. It's not coming from the input. So don't think of it as current flowing internally from the input to the output. The current is really flowing from the power supply to the output, but the inputs are telling it what to do. So, okay, so now we want to wire it up. So this is our first example of a so-called DIP, dual inline package. Yeah, so DIP. Okay, so dual inline package. So you have to be careful to connect this on the breadboard in such a way that, first of all, when you push it down onto the breadboard, you don't want to bend any pins. And second, you want to make sure you don't accidentally shorting 1 and 8 together or 2 and 7 together or so on. So you have to plug it into, there's a special place in the breadboard where you can plug in a DIP package. We'll see that as soon as I switch cameras in a minute. And then you always have to remember to connect the power. So here's positive power on pin 7, negative power on pin 4. And then you should always look and make sure there's a negative feedback path from the output at pin 6 back to the inverting input at pin 2. And you want to make sure you're doing something with the non-inverting input. And then for now, pins 1, 5, and 8 are not used. We will next week briefly use pins 1 and 5. And then you also want to make sure you correctly identify pin 1. So if you look at the writing on the chip, then you'll see the writing is readable when it's in this orientation. If you put it in the wrong orientation, the writing will look upside down. On many chips, there's like a little indentation on one side, basically on the side that has pin 1 on it. The chips that we have don't seem to have that feature, but the chips that we have do have this feature. There's a little marking indicating pin 1. So you want to make sure pin 1 is at the bottom left corner. Okay, so now let's switch over and take a look at what I wired up on the breadboard. Okay, let me show you the way I like to wire these things on the EE board. So I have this power bar up here on the top. The red power rail on the top I use for +9. And the way I get +9 up there is I go from V power plus up to this rail up here. And then I like to use the red rail on the bottom for -9. And the way I get there, I go from VP minus to at -9. And then I like to use the blue power rail on the bottom for ground. So I go from this thing that has just the minus sign, that's a ground, with a little black wire. I like to use red wires for power, black wires for ground. So I have a little black wire that goes over here for ground. And then, okay, so then I have this is my waveform generator. So this blue wire is going from waveform generator channel 1 over to this little column here. And then I have scope channel 2 observing the input. Okay, so the blue scope channel 2 will be observing the input signal. And then we have scope channel 1, which is the yellow scope channel, and it's observing the op-amp output. So we'll go around the op-amp in a minute. And this is the 5, it's actually I think 4.99 kilo ohms. So this is the 5K resistor, it's really 4.99K resistor, going from this little column where this little column basically corresponds to what you see up here called in. And then this little column is pin 2 on the op-amp. Okay, so then let's just go around the op-amp. So pin 1 is the bottom left, so there's nothing connected there. So there's nothing connected in this bottom left column. Oh, by the way, you see this little horizontal area. So this is designed for a dual inline package. So you put half of the pins just one row above and half of the pins just one row below. And that way, you see, this doesn't get shorted out to this. So if you plug it in the middle of an area like this, then you end up shorting pin 1 to pin 8. You short pin 2 to pin 7 and so on. You don't want to do that. So you want to connect it across one of these. So all of the places where you can connect a dip are these little things that have the ridge. So pin 1, there's nothing connected. Pin 2 is pretty busy because you can see in the little schematic up above that I have, let's see, the right-hand side of the 5K resistor goes there. So we have that. And then we have part of the capacitor goes back there. And what you can see doing that is because it's one of these, it's not just an axial lead device. So that connection is made with this little blue wire. We'll see that in more detail in just a minute. And then there's this great big 1 mega ohm bleeder resistor. So it goes from pin 6 back to pin 2. Okay? And then how is the capacitor connected? So remember, we didn't have a 50 nanofarad capacitor. So we put two 100 nanofarad capacitors in series with each other. So here's pin 6 to an otherwise unused column. And then there's that same unused column to this column, and then the blue wire comes back. So this is like, here's a 100 nanofarad capacitor going from pin 6 over to a spare column. That same spare column, then we have another 100 nanofarad capacitor going over to yet another spare column, and then we have this little blue wire going from there back to pin 2. Okay, so we made that connection. Okay, so that was pin 1. Pin 2. Pin 3 is the non-inverting input, which is connected to ground. I have a black wire connecting that down here to ground. And then pin 4 is no connect. Pin 5 is no connect. So you can see the capacitor is jumping over that, but there's nothing connected on pin 5. Pin 6 is our output. So you have this big feedback resistor. You have these capacitors we just talked about, and then you have the channel 1 scope probe looking at that. And then pin 7 is positive power, so that's this little red wire going up to +9, and then pin 8 is not connected. So I like to use red for power, I like to use black for ground, and then I like to use green and red to do other connections. Sorry, I like to use green and blue to do other connections. And it's always a good idea to kind of make a little trip around the op-amp and make sure you see what's connected at each pin, make sure it kind of agrees with what you expect. And then sometimes it's also useful to take like you could take either the scope probe or the multimeter. And sometimes if your circuit isn't working, what I like to do is connect so I have these two little wires that come in from the multimeter. I'm going to connect one of them to ground. And then I like to go around, and the first thing I want to check is that my negative power is good. So that's pin 4. And it says minus 9.06 volts, okay. I want to check my positive power is good, so I'll come up here to pin 7, and it says plus 9.04 volts, that's good. And then another thing it's always nice to do, if you have a circuit that has a virtual ground, you can check that the virtual ground is grounded, so I'll check pin 2, and if the op-amp feedback is working properly, then it should be sitting at ground. And it says it's a little less than 1 millivolts, so that's basically ground. And pin 3 is explicitly grounded, so that should be ground. All right, so that's about all I can do, I think, with the voltmeter. So sometimes it's nice to do that. I mean, you don't have to do it unless something is squirrely, but if something seems not to be working, then that's one of the first ways I debug it. Okay, now let's look and see if the output looks like what we expect. Okay, so you can see my waveforms here, and maybe before I do that, so we have power supplies, there's master enable, we have V plus at 9 volts, we have V minus at minus 9 volts, okay. And then wave gen, we have a square wave, channel 1, 500 hertz, amplitude 1 volt, no offset. And then we go over to scope, and I'm using scope channels 1 and 2, and I'm triggering on channel 2 because I put my input signal on channel 2. And okay, so the input is this nice square wave, and then the integral of a square wave is a triangle wave, so that seems to make sense. And then we could even ask whether it makes sense quantitatively. So the RC time constant we have here, so we have dV out, right, so dV out by dt should be minus V in over RC. And that RC time constant is 50 nanofarads times 5 kilo ohms. So 50 nanofarads times 1 kilo ohm is 50 micro, and then another factor of 5 is 250 micro. That's a quarter of a millisecond. Yeah, so we have RC is 250 microseconds. So then 1 volt per 250 microseconds, which would be like 4 volts per millisecond. And then if we look at this waveform here, actually that kind of makes sense. So it goes from plus 2 volts to minus 2 volts in 1 millisecond, and then it goes from minus 2 volts back up to plus 2 volts in 1 millisecond. So on the horizontal scale here, that's 0 milliseconds, 1 millisecond, 2 milliseconds. So it's half a millisecond per division. So I think that makes sense. So the slope is good. So it's 4 volts per millisecond slope for a 1 volt amplitude. Yeah, so plus 1 is a slope of plus 4 volts per millisecond, and then minus, no. Minus 1 is a slope of plus 4 volts per millisecond, and plus 1 volt is a slope of minus 4 volts per millisecond because of this minus sign here. Good. Yeah, so I think that all makes sense. So let me just pause and take a quick look at the instructions. Mainly what I wanted you to see here, though, is I wanted you to see especially how I set up the wires on the breadboard, because I think if you can try to wire things neatly, then it just makes it easier to follow, it's easier to understand, it's easier to ask us for help. So here's the input to the integrator, and then there's the 5K resistor, and then there's the inverting input of the opamp. Oh, you can't see what I'm pointing at. Yeah, well, we went through this. So here's the input to the integrator, and here's the inverting input of the op-amp. The non-inverting input of the op-amp is grounded. And so there's a lot of action here happening at pin 2. So this 5K resistor is going in here. There's the 1 mega ohm bleeder resistor, kind of a feedback resistor. Basically, bleeder resistor is coming back from pin 6 to there. And then there's also this kind of path from this pair of capacitors back to pin 2. And there's also a fair amount going on at pin 6 because you have that big resistor, you have this pair of capacitors connected there, and I also have the scope probe watching the output there. I guess one more thing I can do while we're here is I can change the input to a sine wave. So then the integral of a sine wave is, well, I guess it should be either plus cosine or minus cosine. So then we can go over and look at the oscilloscope, and we see, okay, the same shape, and it's shifted by 45 degrees. No, same shape and shifted by 90 degrees. Shifted by 90 degrees, so I think our sine becomes either plus or minus a cosine. Actually, I worked out the math on the Slack channel, so I won't worry about working it out in detail here. And I think, yeah, we even worked out on Slack what happened because of that factor of RC. I think when you make 2 pi f RC equal 1, then you get the output amplitude is the same as the input amplitude. So you can, I think you can also see that happen if you want to by adjusting the frequency a little bit. So I just changed the frequency of the sine wave from 500 hertz to 635 hertz. So I think at 635 hertz you get 2 pi FRC equal to 1. So then you should, for a sine wave, get the output amplitude the same as the input amplitude. And sure enough, it looks as if the output amplitude and the input amplitude are the same here. So, okay, I think that's all we will do here for this is for part 4 of lab 8. That's the opamp integrator.